Welcome everyone. Today we'll explore how SymCC revolutionizes symbolic execution by eliminating costly interpretive layer. In this talk, I'll talk why compilation significantly boosts the speed and coverage of bug finding efforts. My name is Priyatam and I'm excited to show how SymCC makes don't inter don't interpret, just compile. More than just a crash catchphrase. Let's move on. Symbolic execution has always been powerful, but often slow due to interpretive overhead. By shifting a compiler-based approach, SymCC reduces performance bottlenecks, allowing us to explore more paths in less time and to uncover bugs that might otherwise go unnoticed. This slide sets the stage why compilation method truly matters for anyone doing serious vulnerability research or large scale software development. Compile for speed. So here's the heart of SymCC, compiling symbolic checks directly into the code. By doing so, we sidestep the interpretive overhead that traditionally symbolic execution suffers from. The result is speedier bug detection and the ability to traverse more paths in the same amount of time. Moving on, this slide, who cares? Of course we do. So this slide highlights why this approach is relevant to advanced students. When your code base is large or security critical, every second matters. Slow tools may not find all vulnerabilities in time, so SymCC's boost to efficiency helps ensure deeper testing within real-world constraints. So let's take a quick refresher on symbolic execution. Symbolic execution systematically explores all possible code paths by treating as symbolic variables rather than concrete values. For instance, if a program reads an integer x, symbolic execution doesn't assign a specific number but keeps x as a symbol, generating constraints for each branch. Whereas in random traditional fuzzing randomly generates mutates inputs hoping to stumble on bugs. It's fast but can miss deep paths where a series of specific conditions must be met. And there are some hybrid approaches like QSIM, which the authors of this paper compared SymCC on various benchmarks, or for example, Driller, one more tool which works in the same area. So these both combine fuzzing with selective symbolic execution. That is, in fuzzing to cover many paths quickly, fuzzing is used, and selective symbolic execution is used to systematically explore harder branches. And one more thing, one more interpretive symbolic execution. The tool KLEE is an example of interpretive symbolic execution. So it runs code in a virtual environment, incurring overhead, whereas compiled symbolic execution used by SymCC injects instrumentation at compiled, removing the layer by layer interpretation. This has often results in significant speed gains. So symbolic execution systematically checks every potential path in a program, allowing us to find deeply buried bugs. In high security software, missing these bugs can be catastrophic. SymCC steps in to help expand that frontier by tackling performance bottlenecks head on. So, so, uh, so the traditional symbolic execution engines like KLEE interpret each instruction, incurring heavy interpretive overhead. SymCC introduces a spin, compiler-based spin, leveraging modern LLVM toolchains for efficiency. And this evolution bridges older interpretive methods and newer and more agile approaches. So the biggest challenge in symbolic execution is path explosion. The number of possible paths scales exponentially with code complexity. This quickly consumes time and resources, leading to timeouts or missed bugs. So SymCC's speed can help mitigate these issues and make symbolic execution more feasible and scalable. So um, the stakes in industry and academia. So companies like Google, Microsoft, and Apple need robust tools to secure their software. Meanwhile, academic researchers push the boundaries of automated testing. Both camps benefit from a faster and more thorough symbolic executor. So SymCC's performance gains directly translate to broader adoption in industry and deeper exploration in research. So the SymCC recipe for speed is what our interest and focus today. So to understand where SymCC's performance gains come from, we need to look under the hood of its compilation-based approach. First, SymCC integrates with LLVM, a powerful compiler framework used by CLang. During compilation, SymCC automatically instruments each conditional branch to capture the decisions that code makes at runtime. This replaces the slower instruction by instruction interpretation you see in older symbolic executors like KLEE. Here's how it works in practice. The SymCC team build a CLang plugin that modifies the IR of the program at every branch instruction, like if statements or loop conditions. SymCC inserts a small snippet of code that locks the constraint to a symbolic state. For example, if x is greater than 100 is a if condition, so 100 value will be stored. This snippet also calls into a runtime library which communicates with a constraint solver, often the same solver used by KLEE. By doing this at compile time, SymCC transforms the original code, into a version that natively knows how to track symbolic paths. This design significantly reduces the overhead caused by interpretation because the instrumentation is built right into the binary. The payoff is much closer alignment between real execution and speed and symbolic analysis, paving the way for deeper and faster path exploration. So, in most interpretive symbolic execution engines, each instruction is executed in a virtual layer, like a miniature CPU, that keeps track of symbolic data and constraints. While flexible, this is extremely slow. So SymCC flips the script by injecting logic directly into the compiled binary. Here's what happens step by step. So we'll see the step by step in detail now. So the branch constraints. When your program encounters a conditional branch, say if x is equal to 42, the SymCC's instrumented code automatically records that x must be 42 for the branch to be taken. The solver communication comes into the place. Instead of simulating the branch in an interpreter, SymCC calls the solver directly as the program runs. This allows real execution while still building a set of constraints describing each path. So this leads to minimal overhead. Because everything is compiled, there isn't a large interpretive loop. Each branch check is basically a function call or an inline snippet that updates the symbolic context. This approach means that CPU is mostly running native code, which is far more efficient than interpreting every instruction. So for large applications with many branches, this difference quickly adds up, giving you the both speed and thorough exploration of possible execution paths. So here is an walkthrough through the uh, instrumented code by SymCC. So as you could see, this is the LLVM bytecode without uh, for a simple function that uses comparison, and yeah, it takes two integers and checks whether the first is exactly the twice second. So this would have couple of branches. So at the every branch there is symbolic symbol is inserted. So these are the additional calls we are making to symbolic parameters. And yeah, moving on. So let's compare the SymCC with the state of the art tool KLEE. So the authors of this paper conducted a series of benchmark tests comparing SymCC to well-established tools such as KLEE. While KLEE remains a staple in academic research, it uses an interpretive model that can become a bottleneck for larger, complex programs. So the key findings from these comparisons include: first, the speed. SymCC often runs significantly faster than KLEE, that is like 2 to 3.5 times on real code. And coverage. So with more efficient path exploration, SymCC often found more unique paths in the same window. So this is a coverage map where blue colors boxes indicate SymCC discovered this path uh, while the KLEE failed to do so, and red color indicates KLEE was able to explore this path while SimCC failed. So it is straightly evident that SimCC is performing better than KLEE when it comes to coverage. So this has so much practical uh, advantages in practical settings like scalability, uh, scanning for vulnerabilities in open source projects, and like contrived puzzle programs that stress test symbolic execution. So this is where we see how the compile time approach pays off. Across various benchmarks, SymCC demonstrated up to 3.5 times the execution speed of interpretive engines. So why does that matter? In symbolic execution, time is everything. The more time you have, the more paths you can explore and the more vulnerabilities you can find. Fewer timeouts means fewer unexplored paths, unexplored branches. This directly translates to higher coverage. And in bug hunting, coverage is king. A single missed path might be hiding a critical security flaw. So with SimCC, testers can push further and discover hidden corners in the same or less time for large scale or time sensitive analyses like nightly automated security scans. This can be a game changer. So, if you can see, you might get a doubt why the speed up was not too much here compared to the speed up in these two cases. So the reason is in OpenJPEG, the code contains fewer complex branch conditions and more computationally intensive routines. For example, image transformations. So the overhead from interpretive symbolic checks is comparatively lower, leading to a smaller speedup under SymCC. On the other hand, tcpdump and libarchive benchmarks are more branch heavy and string or packet parsing oriented, so causing interpretive executors to incur greater overhead. Hence, SymCC's compile time instrumentation yields a significantly larger performance gain for these targets. So let's dive into more visual data. So typically we look at two main plots. So previously we have seen SymCC versus KLEE comparison, where SymCC had higher coverage and better coverage than KLEE. While we are comparing with QSIM, uh, you could see the red and blue grids are roughly the same. So out of 47 programs tested, 29 programs um, in 29 programs, both KLEE and both SymCC and QSIM discovered the same paths, while SymCC found 47 more uh, programs, whereas QSIM performed better in 40 other programs. So, so as the code complexity rises, interpretive approaches slow down dramatically. So moving on, beyond the raw numbers, these results translate into real world benefits. So the real world benefits are faster bug detection. If you can test more program states in a shorter time, you are more likely to catch critical bugs earlier. And one more advantage is in-depth checks. When performance isn't a bottleneck, you can push further into complex code logic like nested loops or multi-layered conditionals. And one more advantage is reduced blind spots. So traditional tools might skip certain paths due to timeouts or overhead. SymCC's efficiency reduces the likelihood of missing subtle or deep-seated vulnerabilities. So this kind of improvement is vital not only for high-impact commercial software but also for advanced research in fields like OS security, cryptographic library validation, and specialized firmware testing. So, as any approach would have both the trade-offs, uh, so we will be discussing more about the limitations now. So SymCC is not without its trade-offs. By instrumenting all these branches at compile time, you inevitably get larger binaries. The code includes extra instructions to handle symbolic constraints. This may be a concern if you have strict memory limits or are testing extremely large projects. Additionally, setting up the Clang or CLang plugin and the runtime library might feel more involved compared to a simple drop-in interpretive engine. For some quick prototype or academic uses, an interpretive tool might be simpler. However, for critical security testing, especially a big production scale code bases, the performance gains often justify the added setup and binary size. So evaluating whether SymCC is right for a given project depends on resources, the nature of software, and the depth of analysis required. So here are some criticism or found in this research. So while SymCC delivers impressive speedups, so external critics, including discussion forums and security engineering blogs, points out several limitations. First, performance focus. The authors center on raw speed and coverage gains. So the critics argue they mostly measure standard benchmarks and mid-sized programs, leaving open questions about extremely large or highly dynamic software. Example, huge web browsers or microservices. Then, limited scale testing. Some web articles mention that there's little data on how SymCC scales to multi-million line code bases. So the large scale integration challenges like memory blow-up or compile time overhead aren't deeply explored in this paper. Then setup complexity. Because it relies on C-lang plugins and a specialized runtime, SymCC can be trickier to deploy than simpler interpretive tools. Organizations with custom built systems might find it challenging to adapt. So then it ignores concurrency. SymCC, like many symbolic executors, doesn't deeply handle multi-threaded programs where concurrency bugs are critical. So the critics suggest that focusing solely on single-threaded branching might overlook concurrency vulnerabilities in real-world software. Overall, the paper's big picture is to prove compilation-based symbolic execution is faster. So the critics said there's more to security testing, like hybrid fuzzing integration or complex concurrency, environment modeling, or incremental analysis that SymCC leaves relatively unexplored. So the key takeaways: the future is compiled. To wrap up, SymCC proves that compiler-based instrumentation is a game changer for symbolic execution by blending efficiency and high coverage. It paves the way for more advanced research and widespread industry options. So, thank you for joining me on this journey to faster, smarter bug hunting. And remember, the future of symbolic execution just might be compiled.